So this presentation is about estimating the population mean using Excel when we do not know the population standard deviation. So this is more realistic than the one in the previous section where we pretended that we did know the population standard deviation. This time we're just going to have access to a small sample, and we'll find the sample standard deviation S, and we'll find the sample mean, X bar, just from a little simple random sample of the population. And this is in modules 13 and 14 of the OLI textbook, and it's in the workbook for the class in the November 2020 edition. It starts on page 441. In a previous topic, we learned how to do this by hand. We found the margin of error using this formula, T star times S over the square root of N. So we needed to find a critical value of T, sample standard deviation S. The little n was the sample size, and we could calculate the margin of error. So this time we'll use, we don't know the population standard deviation, but we can, from a sample of data, we can find the sample standard deviation using stdev.s. And then we can plug that back into this formula, or we can plug it into an Excel function that will do this little bit of arithmetic for us. Look up the T star, multiply times S, divide by square root of N. So we can do all that in one step. And in the workbook over here, I've listed out those steps for how you do this in Excel. I've also got instructions over here for how to use the TI-84 calculator. But in this video presentation, I just want to demonstrate how to do it in Excel. So coming over here to the spreadsheet. So this looks very much like what you saw in the previous video. It's just now we say unknown sigma. When is it useful? We want to estimate the population mean of a random variable. We don't have access to the whole population. So you're going to get a sample mean, and you wonder how close is it likely to be to the truth? What's the distance between the sample mean and the population mean? What's that distance likely to be? And so when does the method work? You don't have to know the population standard deviation, but you still have to satisfy these two validity conditions. Unfortunately, they're just the same as they were for the Z interval. When we did know sigma, you need to have a simple random sample of the population, and the variable needs to either be roughly normal or the sample size has to be big enough to compensate. So the low 30s would be big enough. So this example problem is just almost exactly the same wording from the previous video. We just replaced the word population standard deviation now with sample. So we're planning to get simple random sample of 16 peanut butter cups. We're going to get the average mass, sample mean weight, well, mass really, okay, of those peanut butter cups, and we want to calculate the margin of error. So we have to decide, are we going to use the Z method or the T method? You use the T method because we do not know the population standard deviation. That's all you think about to make that decision. Is it going to do Z versus T? That is, do I know the sigma or not? Once you've made up your mind which method to try, then the question is, are the validity conditions met? And yes, in this story, we are planning to get a simple random sample, 1. And 2, even though the sample size is small, we're told in the story that the distribution is normal. Okay. So, the confidence level in the story is this 95%. Okay. So the significance level is 1 minus that, or 0.05. That's alpha. This letter here, this lowercase Greek letter alpha, looks like a little fish. That's what that is, the significance level. So in order to use the Excel function, it's going to be confidence.t, and you put in the alpha, the sample standard deviation s, the sample size n. So for this problem, I'll type equals, start typing confidence. It gives me choices. I pick the confidence.t. I put in the alpha, that's this 0.05. I'll just click on it. Sample standard deviation in the story was given to be 2 grams. Sample size was 16. Close the parentheses. That's all I have to do. I say enter. I'll round it off. I don't want to show a lot more digits than, well, however many digits I got in my sample standard deviation. Like, let's change the problem a little. Like if this had said 2.1 grams for the sample standard deviation. Okay, then down here, I'd go 1 digit beyond that. I'd say, okay, my margin of error was 1.07 grams. I show 1 digit more. No, I don't. I show the same number of digits. There we go. The same number of digits past the decimal point that I had in my sample standard deviation. That was, I was about to say one more. Where would this 2.1 grams have come from? You get this, you use stdev.s to get the standard deviation for your data. In your sample, your 16 peanut butter cups, you get the sample standard deviation, and you'd show 1 digit more than the original data's accuracy. So if the original data was accuracy to the nearest gram, then you'd show the nearest tenth of a gram here in your sample standard deviation. It's a sample statistic, and almost all of those are reported with just 1 digit more than the original data. And this E is also a sample statistic. It's the same rule. It's the 1 digit more than the original data, the same as the S. That's 1.1 grams. You include the units of measurement, grams. And that's your answer. And then how do you use it? Well, if you get your sample mean, now you know that the real true population mean is probably not more than this distance, 1.1 gram, away from the truth. So the truth is probably between x bar minus 1.1 and x bar plus 1.1. That x bar comes from your data. You just average up the weights of your 16 peanut butter cups, and then the true population mean is probably not too far away. And that's it. That's all for this topic.